In this video, we'll learn about moment generating function, which is basically similar to Laplace transform of the joint PDF. It is sometimes easier, quite often easier to work with the moment generating function than characteristic function. So moment generating function is similar to Laplace transform, and characteristic function is similar to Fourier transform. If you have a pair of random variables, the joint PDF is fx y of x and y. So moment generating function is expected value of e to the power of s1x plus s2y. So is exponential of a linear combination of x and y, which is a double integral that you know the details. And then we call these joint moment generating function. So which is, because it's like a Laplace transform, that has one-to-one relationship with the joint PDF. So it represents the distribution. Why we call it generating function? So we'll see about that. So the first step is the definition. So this is the joint moment generating function of a random pair, or briefly the MGF of random vector xy. So which is expected value of e to the power of s1x plus s2x. S1 and s2 could be two different real numbers, or they could be complex number. If these expected value, if these double integral converges, we call it moment generating function. It's not all distributions, they have a converging moment generating function, similar for the characteristic function. So a very simple theorem says that if you have the moment generating function, if you calculate the derivative of this function with respect to s1 k times derivatives. So the partial derivatives, one times, twice, etc. in cascade, and r times derivatives. This is with respect to to s1, and this is with respect to s2. And then once you calculate these derivatives, replace s1 and s2 by 0, then you get the moment of xy of order k and r. So the proof is very easy. So the proof comes from here, because if I calculate, let's say, derivative of phi x y with respect to s1 and s2, if I take the derivative of this with respect to s1, what I will get? I will get derivative with respect to s1 of expected value of this function, e to the power of s1x plus s2y. This derivative is a linear operation, and this expectation is an integral. So basically you could, this differentiation, you can take it from your calculus, put it inside. So what you get expected value of differentiation of this function. So if you calculate partial derivative of these with respect to s1, what you get, because this is going to be equal to, this is equal to e to the power of s1x, e to the power of s2y. So if you calculate partial derivative of these is partial derivative of this, then you get one extra x, and then you get s1x plus s2y. Now, if you take derivative of these again and again, let's say ka times, if you take ka times derivative, you get ka here. Or if you take now derivative of these with respect to s2, let's say r times, then you get also y to the power of r. Each time you calculate derivatives, you get one extra y here. Now, if you replace here, if you replace S1, S2 in both sides of this equation by 0, if you replace this one by 0 and this one 0, this becomes e to the power of 0 and becomes equal to 1. So these will become expected value of x to the power of k and y to the power of r, because these will become e to the power of 0. So if you replace this s by s1 and s2 by 0, okay? If not, if you don't put it that, then this is correct. Okay, so okay, let's say you could replace s by s1 by 1 and s2 by minus 1. So you get another moment. So if I ask you to calculate mean of x, y to the power of 2, and then e to the power of x minus y, then you have to get one-time derivative of this one, a one-time derivative of this one with respect to x, sorry, s1, 2 times derivative of this one with respect to s2, and then replace s1 by 1 and s2 by minus 1. Then you get this moment. So you could generate and calculate various moments of x, joint moments of x and y, using the moment generating function very easily, taking the derivatives and so on. So these derivatives at 0, they give you the coefficients of Taylor series expansion of the moment generating function. So in summary, the partial derivatives of the joint moment generating function k times with respect to s1 and r times with respect to s2 successively, and then submit s1 and s2 both by 0, then you get the moments of x and y of order k and r. Now, another thing you may do is that you know that e to the power of a is equal to summation of a to the power of n divided by n factorial, and n equal 0 to plus infinity. Now, if you replace this a by s1 plus x, s1x plus s2y, okay, so you quickly get this expression. Now, this expression, you know that this is like you have another equation. If you remember, a plus b to the power of n is equal to summation of k equal 0 to n. N chooses k, and then a to the power of k, b to the power n minus k. So this is Gaussian polynomial, and this is Taylor series expansion of an exponential function. So now you can once you replace this is your new a, this is b, and so on. So you could have this expression, and this is a double sum, so you could put also this one here, and because this guy is n factorial divided by k factorial and then n minus k factorial, and then you have 1 over n factorial. So these and these simplifies, and then you could have this expression. So if you take expectation of here, expected value of this one, this becomes the joint moment generating function, and these are constant, okay? So the only two things are not constant. So the mean of x to the power of k and y to the power n minus k obviously is denoted by m x to the power of k and y to the power of n minus k. So this is what we get this expression. So you see that the Taylor series expansion of this one, the coefficients are your moments. So the moment generating function by its Taylor series expansion generates the different moments of your random variable. So if you write this one for let's say n equal 1, 2, 3 and k equal etc., so you'll say that. So it's equal to 1 plus mean of x, mean of y, and then 1/2 of power of x, power of y, correlation of x and y, and so on. So as example for using moment generating functions, assume that you have two zero mean jointly normally distributed random variables. So from here, the joint distribution, you can write the expression. So From here, I may ask you, oh, prove this one. So it's very easy to do it in moment generating domain than in using PDF. So the proof is very easy because the joint moment generating function of this random variable is equal to this expression, where this is the variance of x, variance of y, and this is the correlation coefficient. And you see that the expression of the joint distribution of normal random variables is much simpler than in PDF domain. Now, if I want to calculate this one, because I have x to the power of 2 and y to the power of 2, I have to take the derivative of these twice with respect to s1, twice with respect to s2, and then replace it by 0. So if you take derivative of this one with respect to s1, what you get again? And then you do it in 4 steps. So 4 times derivative, twice with respect to s1, twice with respect to s2, and then replace it by 0. Then the result is going to give you these guys. So if you do that, you get what you want.